So thanks to theorem 2.2.2, indeed we can say that if degree of G, in the degree of G plays an important role in the parameters, and if the degree of G is strictly less than n, indeed the evaluation map is going to be injective. So corollary 2 to 3 say that if we suppose that degree G is strictly less than n, then the evaluation map is also injective, and we have an n-degG code over FQ the dimension L of G, which is bounded below degree G plus 1 minus G, and the minimum distance D is bounded below n minus degree D. So these two, indeed these two inequalities shows us D plus K is bigger than or equal to length plus 1 minus G. So in some sense, it's kind of similar statement, like a similar inequality, like in the singleton bound. And additionally, if we suppose that degree G is strictly bigger than, the degree G is large now, so that means it is bigger, is strictly bigger than 2G minus 2. Indeed, the dimension can compute directly as the degree plus 1 minus G as a consequence of the Riemann's theorem. And if we denote the basis of a Riemann-Roch space L of G by the functions x1 up to xk, then the matrix which contains the rows, which contains the evaluations of these functions at given places as rows, will be a generator matrix of algebraic geometric code. And we can show that if the degree is strictly less than n, dimension of the dimension of the Riemann-Roch space of G minus D is going to be 0, because in this case, degree of G minus D will be strictly negative. By the way, here note that the degree of D is n, because D is defined as a sum of the n rational places. So, since the kernel of evaluation map is trivial space, this shows us relation D is injective. So there's a isomorphism between the Riemann-Roch space of G and the AG code. And for the parameters which appears in the part A, we can directly use the theorem 2.2.2, so the previous theorem, where we show the minimum distance is bounded below n-degree d, and because of the injection, we get the dimension of L of G. And by Riemann's theorem, we know that the dimension of a divisor is always bounded below its degree plus 1 minus G. And for part B, if we additionally suppose that if our degree is large enough, this allows us to apply Riemann's theorem directly. So we can compute the dimension as degree G plus 1 minus G. And due to the injectivity of the evaluation map, by using linear algebra, we can easily conclude that for k linearly independent vectors in the Riemann row space, their images produces k linearly vectors of length n after their evaluation at this given distinct places PIs. So, and this is obviously is going to be generator matrix. And here, just let me note that due to these two inequalities which appears in part A, we can see that the dimension and the distance is bigger than or equal to n plus 1 minus G. And on the other hand, by the singleton mount, we know that this sum is bounded above n plus 1. So we can easily conclude that as long as the genus is 0, our algebraic geometric code is necessarily maximum distance separable. And indeed, again, thanks to this corollary, to be able to get a meaningful bound for an algebraic geometric code. So that means to be able to get a positive integer in this difference, obviously, we need to suppose that degree G is supposed to be strictly less than n. Otherwise, we get the minimum distance as 0 or negative, and it doesn't make sense. So this is why we will define what is called the design distance. So the integer which is defined exactly as the difference n minus degree of G, which is denoted by D star, is called the design distance of the code, algebraic geometric code, which is defined by the divisors D and G. So, and by the corollary part A, corollary 2 to 3, in that we always have that the minimum distance of an AG code is bigger than or equal to design distance. But the interesting case when the minimum distance is strictly bigger than this star, so this can be also the case. And indeed, the next remark will shows us when we get equality, so the worst case for the minimum distance, or do we get better than the design distance? So for this purpose, let me suppose that the Riemann space of G is not trivial, so that its dimension is strictly bigger than 0. And d star n minus degree of G is also strictly bigger than 0, so that means degree of G is strictly less than n. Then indeed we can see that the minimum distance of an algebraic geometric cause is exactly n minus degree d if and only if there exists the effective divisor d prime, which is less than or equal to d with respect to partial order in the divisor group, which has the same degree of G, and the Riemann space of the difference of the divisors G and D prime is non-trivial. And indeed, in order to see that, so first let me suppose that our minimum distance is exactly this design distance. Suppose d star is this, so that means there's a code word in C whose weight is exactly n minus degree G, and this allows us to consider a non-zero function in the Riemann space such that use image under the evaluation map has exactly n minus d0 components. Is exactly n minus d, so that means n minus d star and by definition of d star we consider d star as n minus degree G, so which is exactly degree G 0 components. And let me denote these 0 components by ij's. So let me say this function has zeros. It places pij's here, j from 1 to degree G. And regarding these distinct places, distinct rational places, let me set a divisor d prime as sum of these rational places. And indeed, we will see that this d prime is the desired divisor d, which has these properties. So first, by the setting of d prime is obviously p prime because it has no negative term. And since all these places lies in the support of d, this shows us d is less than or equal to d. And its degree is the degree of the sum of these rational places, so pi1 to up to pi degree j, and in total we have degree g rational places which appears in the d prime. And finally, since by the assumption this function says zeros at pij's, it means their valuations at these distinct places are strictly positive. And since the function x from it is chosen from the Riemann space of G, we can see that this non-zero function lies in L of G minus D prime, and indeed this shows us dimension is also strictly positive. And conversely, if you suppose that there exists a divisor d prime, which is less than or equal to the given divisor d, that has the same degree of the degree of g, and the Riemann space of the difference g and d prime is not trivial, then in the theory we want to see that the minimum distance of d is supposed to be n-degree g. So that means there exists a code word of weight n-degree g. And because of this non-trivial space, this condition, we can consider a function y in the Riemann space of g minus d prime. And let me observe the weight of its evaluation, its image under the evaluation map. So since we choose y from this, since y is from this Riemann space, so that means the principal divisor is bigger than or equal to d prime minus g. So its minimum distance indeed, its weight indeed n minus d prime. So that means it has zeros at d prime. And indeed, it shows us by the assumption on the degree of d prime, this is equal to n minus degree